So this is a very, very boring talk that I'm going to give you today, of course, because, you know, GNU, this is the original title, GNU Radio-based SDRs for isotopic and isomeric mass and lifetime measurement in heavy ion storage ring, and boring, boring, boring. But then I was thinking, okay, Eric Blossom gave us such an inspiring talk at the beginning, so maybe I should change the title to something like Reaching to the Stars using GNU Radio. So I mean, why not, right? So, but there is a bit of truth in this, because this is from all of the, you remember from the nice tour that Jens gave yesterday, and also some of the people that were with me. We were walking around the GSI tour, GSI facility, and to see what is happening. And also from the very beginning talks of Peter Spiller and also Jens, you got this information, or got this taste of how GNU Radio can actually help us on all aspects of the research, fundamental research here at GSI. So what does it actually mean? Basically, we are interested in elements, and elements, we want to know. Everybody knows about the standard elements. This is the periodic table of elements that you everywhere see in the schools and the universities. So this is a very good thing, because it contains all of the elements according to their chemical properties. But there is some information that is missing in the standard presentation of the elements, and that is that every element exist there because of the certain number of protons that they have. But what is much more important is that they can have different number of neutrons, and this is called the isotopes. So that basically every element that you see here in the table on the left side has basically a number of different isotopic configuration. That means, for example, lithium has only 3 protons, but it can have 3 neutrons. It can have a 4 neutron version, a 5 neutron version, so that you have the overall lithium 6, lithium 7, lithium 8, and so on. So if you basically make a 3-dimensional map of this picture on the left hand, you can see here that this picture that you see here is just one layer, that every element in fact has a lot of different isotopic configuration. And that's very important for us from many very different aspects, from the biological aspect and also from the point of view of stellar evolution. And that's one thing that people in the nuclear physics and nuclear astrophysics community very much like. So instead of using this picture on the right side, and people redistribute this map into a much more readable map, which is called the nuclear chart. And the nuclear chart immediately tells you all information, because it tells you that if you have the number of neutrons here and the number of protons there, you have seen this picture in Jens' talk at the very beginning, you see that all of the things that you saw in the stable isotopes, they are here in the black line. And then, but you have for every element which is named here, you have basically a distribution of different isotopic configuration that you can have. So you can have a more proton-rich, you can have a more neutron-rich. The blue ones means that they have more neutrons. The orange ones means that they have more protons. So it's a very important picture, because all the nuclear physics, nuclear astrophysics community can immediately see a lot of things here. So you can have the super heavy elements here, GSI expertise. You can have the proton-rich. You can see how the things. Why is this only so narrow? Can it be? Why there is nothing here? Why there is nothing here? Because you cannot have an element that has a lot of neutron but has not so much proton. So there's a lot of information here. And of course, if you like, you can have a free, there is a free app for Android and iPhone. You can just download it and just play with it. You can zoom in, zoom out. It's very nice. So I hope everybody knows what IAEA stands for. No? International Atomic Energy Association. Yeah, so that's from the United Nations. So this is the official app of the United Nations for this. But this is so important for the nuclear physics community that people even don't have the time to spell out the nucleic chart. They usually call it the nucleic banana. So this is the jargon, the official jargon in the community. But where do actually the elements come from? And that's the most important question that we are interested in. Because the core of the the core of the elements, there are many, many different possibilities. So we start, so the so-called the Big Bang nucleosynthesis. So you have to have a starting point, and this picture is one of the most stolen slides in the in the community of nuclear astrophysics. So this is like a mixer jar of universe. So you can imagine that everything there is in the universe is inside this jar, and here outside there is nothing, because the whole jar basically contains the space and time, whatever, you know. So, but that's the only way you can actually present this, is that you have different stages of the universe, the evolution of the universe. At the very beginning, you have the Big Bang. You have enough pressure, you have enough temperature where you can create the very first element. But then the universe gets very fast, very cool, so you cannot process. And then you have the first stars, which are so-called low metallicity stars, and then then later you get more on and on and on. So until you get the different stars and galaxies and formations. So basically, the stars are the birthplace. The stars are the birthplace of the elements, and that's where we are. What we are interested to do is that we want to know that across the nucleatic chart, what kind of process, be it like accretion, white dwarf, we have some burning stars, we have some supernova explosions, type 1s, type 2s, we have neutron mergers. So how exactly this nucleatic chart is being processed. And this is the same nucleatic chart, as you can see here, that there are actually several different processes in action. So you have the Big Bang nucleosynthesis, you have the S process, the slow process of neutron capture that can happen inside a neutron wind in the universe. You can have the rapid process. So if you have a site which is just standing there and suddenly a neutron star explodes, suddenly a supernova explodes, and there's a huge amount of neutron wind, then this thing starts to burn. But as you can see here, if you look along this line through the thing, that's called the value of stability. Basically, you're looking at here. And this means that the way that the nature is producing the elements is just going staggering. So what it does, it never goes up like that. So you never start from hydrogen and helium and suddenly create gold or titanium. So what you do is that you just stagger. You go a little bit right, then fall back. You go right, you go fall back. You go right, you go fall back. So this kind of staggering mechanism. And this is very easily visible here, if you can see here, that these are actually higher in energy. That means people try to go up and fall back. The evolution of the elements always goes forward, but it never goes on the valley itself. It just goes up and down and up and down and up and down and up and down. And this means that you have to do this, because otherwise you cannot just go a straight line. The problem with this is that the stages where the elements are trying to evolve can be temporary. It's as if you want to try to climb a ladder, but your bars here, any of these bars or any of these holes, is just available for you for a couple of milliseconds. So you either manage to climb up within that couple of milliseconds, or you cannot reach that energy level. So that means if you want to create a gold, you have to have a certain energetic path through the isotopic configuration, which allows you to actually traverse that line of energy. And not only that you can do it, but you can do it in the right time. That's why, apart from the nuclear mass and the reaction cross-sections, what is very important for us is the lifetime of the isotopes. And that's what we want, and that's what we want to do with GNU Radio at GSR. So this is GSI, you know this. This is the GSI fish. This is a very long-lived, rare species here at GSI. It used to live here, but since Ralph started to build his FCC here on this building, it's a running joke. So this building. This is being is being built here right now. There used to be a pond over there, so this fish used to live there. But everybody has promised the fish to get a new pond in the new fair. So that's that's another thing. So this is exactly the same picture again. So you know that we have the source and accelerator and everything, so you know already this picture. Again, the same. So what we do is that we want to inject into the ESR, and the ESR is now shown here in a much larger picture. And we have here a couple of non-destructive detectors that you can see here. By the way, I also teach the art of self-citation. So in principle, if you're interested, it's $50 an hour. So so we are using this non-destructive detectors around in order to record. So we let the particles, we inject the particles into the storage ring. So we let them go around as long as they want, and as suddenly, if there is a kind of a lifetime, there is a kind of a disintegration, then we can exactly measure this. How do we do this? We have a chain of signals, analog signals, low-pass filters, band-pass filters, and everything. And of course, we use data acquisition. Unfortunately, up to now, the standard commercial ones, I have sinned. This is running with LabVIEW. These are some good spectrum analyzers, to be honest, but the problem is that they are not scalable, and they are very, very expensive. So how does a picture like that look like? So this is a spectrum of all the possible lines that we can see. This is a two-dimensional. Two-dimensional spectrum, and you see all possible nuclear isotopes that you can see after an injection into the storage ring. You can zoom in. You can zoom in to get more data. You can even zoom in to see the isomeric contamination of the individual isotopes. So what is so nice about this thing is that if you watch this two-dimensional spectrum, which is acquired by an RF signal from those detectors, for example, from this detector, you can make a waterfall diagram like we had this here, and this waterfall diagram shows that time. Okay, in this case, time is coming from up to down. So you see that one particle, actually two particles, are coming down, and suddenly, after it's a short time Fourier transformation, it's a short time Fourier transformation, it shows that suddenly one of them decays. So that basically the first time signature shows the lifetime of the first isotope, and the second one that. And if you continue doing that, even with a so this is basically the same position. So if you continue doing that with maybe a little bit more sensitive devices, you can even much more exact say, okay, these were two particles here. One of them, after about a second, one of them decayed, and after a couple of seconds more, the other one decayed. So you have two. This is basically the transition from one of those blocks. If you imagine the value of a stability, it was just whoop, just slip down one block from here to here. So one isotope changes its nuclear constitution from one thing to the other. So this has a lot of information for the physics community. Everybody is very happy about that. But of course, we do all this analysis using Python. We do a lot of calculation in the green cube and everything. But where we have also analysis code on thing. But where does this journey go? These are some possible detector positions that we are planning to do in the collector ring at FAIR, and this is where I was actually going to approach Jean-Michel here for this, because this is very much relevant to your to your talk that you just had before. We are going to, of course, we're not going to put detectors all around this place, but at least a couple of places. So we are, of course, we would like to increase the measurement accuracy by correlating signals from different detectors. Exactly. So this matrix, as Jean-Michel was showing, is basically carrying information for us, which is relevant for the exact time measurement. So we really need a white rabbit-based, hopefully GNU Radio that can take the signal, basically observe the same beam from 4 different locations around the ring, and by correlating by the phase information of these things, we can actually get to much more accuracy in the measurement. So we have also my colleague here, Dr. Chen Wang. She's also here to help us in this respect. So some personal history at SDR. Of course, back in 2008, it took me about 6 months to make this SDR board from scratch, from schematics and PCB, 100 micron technology, programming the Altera thing. So it took me a lot of time. It's still working because at that time I started in the RF group actually here at GSI. Even at that time, I don't know which version it was, I tried to use the GNU Radio in 2008, but I really couldn't manage to connect it to my self-made board, and so basically I switched to the commercial ones up to now, which I hope that I can come back. And this we have done. We've got some experiences, and thanks to Alexander, Ralph, and all other people who have, and also colleagues from the ACO department who have created, and also the electronics department who have created the picoscopes, and also the Lime SDR is put into this kind of very nice things. We actually were able to do the first measurements using this. So this is a very beautiful measurement. So as you can see here, this is the thorium. This is a thorium beam, which is standing on top of a couple 4 components. Basically, it's a protactinium, we have the actinium, and a little bit of uranium also on top. So that means you can see this picture here already makes a lot of people very, very, very happy, because this has never been seen before. This is as if you can imagine that this is basically you have a beam of thorium going around, and then you have all these other components that they are constantly taking over and coming back, and taking over and coming back. Basically, they are, for RF people here, they are basically fighting against, the electron cooler is basically fighting against the bunching potential inside the basically phase potential or the bunching potential inside the storage ring. This is an amazing phenomena, so this itself is worth of publishing by itself. One of my colleagues is working on this. Forgot to thank him. That is Konstantin Mohr. I forgot to put his name here. So what we want, future ideas. So what we want is, we are very much interested in one flow graph, one computer which runs actually the GNU Radio flow graph. It can have the timing connection to FAIR, GPS connection. We have of course, we have the connection to the high performance computing of GSI, thanks to Thomas Stibo and other people, where we can continuously throw basically right into the luster. We are looking forward to have connection to the accelerator network, thanks to, I think Hanno is there, thanks to Hanno and his colleagues. So, and if we could basically put some picoscope units and SDR unit in one big top thing, that we can control everything through one big genograph, that would be amazing. So this is, for example, one thing that we have been testing, and this is going to be the 2025 experiment as well. So you can see that in the previous experiment, we were able to achieve the very, very high resolution that is equivalent of 100 keV energy difference between the nucleus and its first isomeric state. And this is so close, that is the 100 kilohertz, that is amazing. So what we want to do is to monitor to see if so this is the ground state, and this is isomeric state. Sometimes it comes, sometimes it doesn't come. So for that, we need GNU Radio. Why? Because 2025 experiment proposal, my boss came to me and said, you know, Shahab, Yuri, my boss, he said, you know what, we are going to hunt for a very, we're here to hunt for a very, very rare isomer. I said, because it comes so, the probability of production is so isomer, that is very low. So we want something that, as soon as we see the isomer, we should stop the accelerator. I said, okay, fine. And they said, what? Stop the accelerator? We have never done that before in the last 50 years of GSI. To see, look at the spectra on the fly, and if you find something, you stop the accelerator to continue measure it. So basically, it's a very, very, very simple GNU radio graph. So you have some kind of source, then you have a condition. Who's a ham here? 1, 2, 3, 4, 5, 6, 7. So everybody knows a squelch. You have the standard squelch. So I just need one source, which is the hardware. It can be this SDR. It can be condition. One branch is continuously writing to disk. The other one just has a squelch. Looks at this picture. If it's one, if it's 1, it doesn't send any signal. But suddenly, if it's 2, it should immediately send a signal. And this is basically like the fencing, you know. So you have there's a fencing line going on, and we were even thinking of making an acoustic beep because these isomers are so rare. We need people to wake up because otherwise they fall asleep during the midnight when they're doing this. So, and just as a matter of fun, since 2020, we are having our experiments simultaneously monitored by our colleagues in Japan and also in Vancouver, in Canada. So this is something that all people from different time zones can actually take part live. So we were thinking about them making a drinking game out of this. So every time there is an isomer, you have to go for a shot. So thank you very much, and I'm happy if there's a question.